So we have come to the end of the system identification module, and we will end the whole course in about 2 more lectures. Today we will discuss what I have written here as practical issues in identification. So we hopefully we want to show that people have sometimes, because academic courses tend to concentrate on algorithms, so people think that the algorithms are everything, but that's not correct. There are lots of other issues before and after you run the algorithms. So all of that have to be compressed in one day's lecture. So we will again talk somewhat philosophically, or take a common sense approach and see what kind of look at identification as a whole, and try to see what other things are involved so that you actually get models which are useful to you. So that's why I thought it's a nice maybe it's good to look at the identification process as a whole. So here is the gentleman whom we want to study, right? The plant. So you have, and here on both sides I have written various issues that are involved in getting the model, right? And they're involved at different stages of getting the model. So these boxes indicate the stages of getting the model. So the first of all, you must understand that the plant is not the only thing. There is this measuring system. So you are working with a measuring system, and essentially you must remember that you are building a model between the measurements. You might think that you are building a model between this and this. You are not doing that. You are building a model between what you measure, what you measure and where you measure this, and between what you measure and where you measure this. Not exactly between these 2 points, right? And there could be, so this measuring system itself needs to be understood, because this measuring system is included in your model. Firstly it is included, and secondly it affects the modeling. So you need to very carefully understand that. And you need to understand what kind of time constants or delays it involves, what kind of sampling rate it uses, what are the biases, drifts which affect it. Then after you got the data out of the measuring system, you kind of came to the computer. So this is like the data acquisition system, and then you came to the computer. So from here the computer starts, you've got those numbers, whatever they are, right or wrong. Then before using them in your algorithm, you don't blindly plug them into the algorithm. You do a lot of processing before you use them into the algorithm, so that you get good results, right? And you typically like to filter things naturally. Just because you can model noise doesn't mean you are going to let in a lot of noise. You will cut out as much noise as you can. So what sort of filters to be used? Sometimes you have to use scale factors. I don't know whether you have ever tried to train a neural network. In a neural network training, if you don't use scaled data, all of which are roughly in the same ranges, if you use one data which spans between 0 and 10,000, and I mean another data which spans between 0 and 0.1, it will be very difficult to train the network because of the interconnectivity. So no set of weights can actually handle such kinds of data whose ranges are widely apart. So you need to scale data to bring them roughly in the same ranges, do your estimation, and then get back to invert that scaling map to actually get back to the realistic values after you have estimated, right? So you need to do a lot of scale factors. You need to do that. After that, you have to form. We have the kind of algorithms we have discussed are linear or pseudo-linear regression methods. So all of that involves forming what is known as a data vector or a regressor. So before you can apply a parameter update, you need to compute the regressor, and that involves a lot of things. For example, it involves choosing your model structure, choosing the order of the model. Even I mean, in many cases, even after this pre-processing, you'd like to do further filtering, as we'll see that the same transfer function, let's say GS, can be written in various ways using a phi transpose theta formulation. Various ways are possible. So to basically what kind of signals you are using in the regressor depends on what kind of state variable filtering you use. This is a new term, so we'll see what it is. And obviously, if you are using instrumental variables, then you need to have your choice of instruments at this time, because the instrumental variable forms the other data vector, that is the instrument vector, which you are also going to use in your algorithm. After having done that, you come to the actual algorithm, which those 3 or 4 equations which will update, which will give theta hat k from theta hat k minus 1. So there you need to choose your algorithm. Every algorithm will involve certain parameters. For example, if you are using exponential forgetting, you need to choose what is going to be the value of lambda. So you need to choose the algorithm parameters, and you also need to see to what extent you can incorporate prior knowledge. If you know that the algorithm is stable, or if you know that its dominant time constant is not more than 10 seconds. If you happen to know this, you must use it, because if at any point of time your algorithm throws up a time constant which is more than 10 seconds, you don't update that, because you are sure that it is not more than 10 seconds. So you need to know how you can incorporate the existing knowledge about the model that you have based on prior experience, whatever. So having done that throws you 2 things. The algorithm gives you 2 things. First, it gives you the theta hat, and second thing, it gives you the prediction error. Both are important, as we have seen, for checking whether the model is right, whether the estimation has been okay, and to do certain kinds of post processing. You may not even like to use this theta hat directly in your application. You may like to do work further. For example, you may like to check whether there has been any common pole 0. If so, cancel it. Why have common pole zeros? Common means you will never get exact match again, whether you are getting pole zeros which are very close, right? So you might like to do model reduction. You might like to do filtering not only on the data. See, all this while you have been doing filtering on the data sequences, YKs and UKs. You might like to do a filtering over theta, because theta is continuously jittering because of noise. But in any given case, you know that the parameter cannot jitter like that. So after you have estimated the parameter, you might like to filter it. So such post processing may be needed before you finally hand it over to the application for use. So there are so many steps which are involved in successfully estimating a model which will serve the purpose of the application. So we will now look at these in sequence. Coming to the measurement system, as I said that you must realize that you are estimating the model between measured variables. So anything which is being introduced into that is coming anyway. So that's not your system model. You must remember that. That's not exactly your system model. If your measurement system is very good, it will definitely approximate the system model. Otherwise, you are using bad sensors, right? For example, common example is if you are doing temperature measurement, thermocouples do not have much time constant, but thermowells could have. Thermocouples are not thermocouples. Have you seen thermocouples? They are just bare wires. You don't put bare wires into a furnace or into a chamber. You typically have a cover on it, sheathed kind of a well on which you put the thermocouple. It is that well which could put a significant time constant between the temperature change which is actually occurring in the furnace and the temperature change that you are measuring. So it might introduce a non-trivial time constant, and if you are estimating, what are you estimating? You are estimating the model between the measured thermocouple voltage and whatever, maybe some heat flow, steam flow rate. So obviously the thermowell time constant is going to come into your model. So you must think of that, and you must eliminate that. If you really want to know that how fast the temperature inside the furnace rises, if I suddenly jack up my steam flow rate, then you need to eliminate the time constant, right? Similarly, you will have actuator dynamics. If you are using the UK values which are there in your computer and think that actually that is going to the plant, it's not going to the plant, it's actually going through the actuator. So there could be a significant actuator dynamics, and when you are estimating, what you are thinking as UK is not really UK. So again, you need to strip off the real actuator dynamics to know what's going to the plant, right? Similarly, there could be delays due to the location of sensor. You don't know where your sensor is put in a pipe. I mean, typically, especially in process control applications, I mean, a lot of time the input is a flow variable, because it turns out that if you want to change pressure, you use flow. If you want to change temperature, you use flow. If you want to change level, you use flow. So flow is a lot of time a very dominant input variable. Now what flow you are measuring very much depends on where you have put your flow sensor, how far it is from the process. It's a pipe, right? So you are going to put it somewhere, and that is going to put a delay between the input and the output. And not only that delay is going to be different at different operating times. After all, what is the delay? The delay itself depends on the flow rate and the physical distance. So it really depends on what is the flow rate that you are using. If you are using a low flow rate, then you are going to encounter a long delay. If you are sending fluid very fast, you are going to have a small delay, right? So such things will come in due to the measurements, inherent dynamics between the measurement and the process variable, both on the input side and on the output side. Similarly, you could have various kinds of sensors, inaccuracies, errors, non-idealities. For example, there could be bias and sensitivity error. Most of the instrumentation guys, spend a lot of time studying the Wheatstone's bridge. A lot of sensors use the Wheatstone bridge, RTDs, strain gauges. What's the biggest source of error on the Wheatstone's bridge? It is the supply voltage variation. If the bridge supply changes little bit, you have a completely different sensitivity. And if you don't nullify that, then basically your sensor gain changes, right? And if you are using a constant gain value, then you are off. So there could be bias and sensitivity errors. Bias, one of the very good examples is cold junction compensation, right? So if you have a problem in your cold junction compensation circuit, then you have a bias in your temperature for any thermocouple measurement. Similarly, there could be noise pickups. There could be significant noise pickups. I don't know whether you have ever done this, but you take a piezoelectric sensor. If you have disturbances and if your shield connection breaks, you have huge noise on the sensor. Any high impedance point will tend to pick up noise in any circuit. So you could have noise pickups because of weldings going on, because of not well maintained DC motor running and there may be brush spark offs, all kinds of things. Or heating furnaces, things which are electrical furnaces, current electromagnetic interference is always caused by current, because flux cannot be created unless you have current. It cannot be created by voltage, right? Magnetic field is created by current. So any high current device you have is going to create electromagnetic interference. So you need to think of that. Loading effects. Sensor readings can change significantly due to loading effects, and there can be non-linearities, or there can be ambient variations, temperature variation. Typically instrument characteristics depend on temperature variation. So you must be aware that the data you are using, the sensor fellow might creep in these kind of errors. So you would like to correct for them before using them in the you must correct for them in pre-processing. So first of all, you must know them. So when you are doing signal pre-processing, you have to you will do some kind of filtering, right? Firstly, so typically process control signals are one good thing about process control signals is that they are very slow. They are sub 1 Hz signals in general, and the kind of noises that you come in mostly being electrical in nature, they are high frequency. So it's relatively easier to separate that noise out using filters. So you need to know the input signal and the noise characteristics before you can design your filter. You also need to know the system time constant, because you don't want to alter, you want to keep that part of the signal which is within the system bandwidth. You don't want to keep that part of the signal which is outside the bandwidth, right? Typically, suppose if you are considering let us say a very large motor, let's say a thyristor driven motor. Now the voltage at the terminals are varying at very high speed. Because they are thyristor driven or because they are semiconductor switch driven, they could be at kilohertz level. But the system time constant is guided by the inertia of the motor. So obviously, when you are trying to model speed variations, you don't need to consider. I mean, your model bandwidth does not cross some hertz. I mean, the system being electromechanical, so you don't have to really model it up to 10 kilohertz, even if you are giving 10 kilohertz input, strictly speaking, right? So actually you can use a much lower time constant filter, even if the input is different, right? So you really don't need to use a 10 kilohertz filter, because a 10 kilohertz filter is going to pass all kinds of measurement noise, which will be in the sensor, which could be in the speed sensor, right? Similarly, there could be for example, sampling time design. Sampling time design depends on what? Sampling time design depends on it depends on the model bandwidth, on the expected system bandwidth. Why? Because if you have, if you know the aliasing phenomenon, then if you have chosen your sampling frequencies too small, what is the problem with aliasing? Suppose you have a system bandwidth which is like this, and not only that, now if you sample it at lower than Nyquist rate, I think you're familiar with Nyquist rates, then what you're going to have is that the sampled signal will have spectrum like this, right? So now if you, so what's the problem? So the problem is not that, in general, especially in control kind of applications, it is not the high frequency inaccuracy of the model that's of great concern. But if you have low frequency inaccuracy in the model, that's of much higher concern. So what is happening? What is the overall spectrum of this? The overall spectrum of this is, actually it is like this, because these two things you have to add up. So you can see that this part, this error is not so important, because you are finally going to put a filter. So this error is not so important. What is important is this error, because the high frequency error of the next band gets folded back onto the low frequency zone. So now you will have low frequency errors, which is not good. So therefore, even before you design your sampling time, you need to remember that it's a kind of a chicken and the egg problem. After all, you are trying to determine the model itself. But to be able to determine that effectively, you need to know certain things about the model. That's why it's so important to have a priori knowledge. And you might like to take up exercises just to gain enough a priori knowledge so that you can design a successful experiment, so that you can get a detailed model. So you need to do it iteratively, right? It's not that nicely you just went there, put your data acquisition, got your data, came home, and then you got a model. It can't be done like that. Similarly, if you're trying to design your sampler, then there are certain things that you need to think about. For example, you need to think about your sampling skew. Typically, it may happen that your sampler is sampling channel 1, channel 2, channel 3, channel 4. So actually speaking, you are sampling channel 1 at time t1 and sampling channel 2 at time t plus delta. Strictly speaking, whether that delta is going to matter or not is, you have to decide. But it is not at the same instant, unless it could be at the same instant, unless you use what is known as a simultaneous sample and hold circuit. If you use a simultaneous sample and hold circuit, then you know, I don't know whether you have seen a sample and hold amplifier, but the sample and hold amplifier has two inputs, and if you give a sample signal, then it will start tracking the signal. The moment you give hold, that value will be held. So the idea is that you have several sample and hold amplifiers on several channels, which have, all of which have a common hold signal. So you hold them simultaneously, so they become held at one point of time, and then you read them sequentially. So even if you are reading them one after the other, the values that you are reading have been held at one instant of time. Now all that may not be important at all, especially for example, for process control applications. It makes AD converter sampling times are of the order of microseconds and less. So a microsecond is not going to matter if you are trying to sample 50 temperature signals in all likelihood. It is so slow. So it's not that you are going to need it all the time, but you might. That depends on your application, right? So you have to be aware of it. Similarly, ADC range and word length. Remember that if you are using an 8-bit AD converter, then you are already introducing quantization noise just by the quantization process. So you have to decide whether you can tolerate that noise and what kind of AD converters you can actually use. But then you have to remember, you know, some people make this mistake. For example, have you ever wondered why in the market there are 64-bit processors, 120-bit processors? Why there are not 64-bit AD converters in the market? You can hardly find an AD converter beyond 16-bit. 18 bits are extremely rare. Generally, people use 10-bit, 12-bit. Why? What stops it? After all, if you know the AD converter circuit, you could add stages, 32 stages. Why not? Why not is because you cannot see, if you have a 5-volt reference and if you have a 16-bit converter, then you have 535 levels by which you are dividing 5 volts. So then one level is what? How many volts? Of the order of microvolts. Now the point is that if your environmental noise is of that level, then what is the significance of the last bit? There is no significance, because it will, if you really see it on an LCD, you will see the last bit always flickering. It has no meaning. So you can artificially add as many bits as you like. Only thing is that the last few bits will become meaningless. That's why you cannot I mean, it's very difficult to have, especially in an industrial environment, it's very difficult to have more than a 12-bit converter. So, but you need to be aware that if you are having a 12-bit converter and if you are having a 10 volts reference voltage, then what's the quantization error you are actually imposing, and what does it mean on the actual variable, because it's getting scaled. So maybe 0 to 1000 degrees centigrade is becoming 0 to 10 volts. So to that extent your reading is incorrect. You must be aware of that. Similarly, you do various other kinds of pre-processing. You could do scaling for numerical accuracy, as we have said. This is an altogether, I mean, this is a different subject, that, I mean, fixed point and floating point computations. Nowadays people sometimes use floating point, but floating point hardware is expensive. We are talking about control problems, so we are looking for typically many of the microcontrollers will have fixed point arithmetic. If you have fixed point arithmetic, you have problems to compromise between dynamic range and resolution. You can't do both. So if you have a 10-bit and if you want to increase your dynamic range, then your resolution will suffer, which actually does not happen in floating point. So a lot of times you are going to use fixed point hardware. So scaling might significantly improve numerical accuracy. So you need to scale your data before you use in the regressor. We have not really talked about these issues. You might find some of these in a standard DSP book as to what kind of errors this kind of scaling can introduce. It's quite mathematical. You might like to do data differencing. That is, don't build a model between y and u, rather build a model between delta y and delta u. If your system is linear, it's the same model, right? So what's the advantage? Advantage is that if u or y had any DC bias, that will go off, because the same DC will get subtracted. Similarly, you might have to do that if you are using a linearized model, because in a linearized model, by definition, it's a model between delta y and delta u, where you have to measure the delta from the operating points. So there is a u0, there is a y0, and your model is always between y minus y0 and u minus u0, right? That's what is the model in the linearized model. So you might like to do that. You will have to remove outliers, signals which are downright improbable, something wrong. For example, if you find that while you are doing the experiment, you are doing it on a shop floor. Some guy came and started doing welding somewhere. Immediately, for whenever that welding arc will strike, you are going to get very noisy data. So you must be able to, I mean, are you going to use that data blindly? No way. So you must remove that data. So such things are needed. And another is linearization of measurement. Sometimes, for example, thermistors. When you use thermistors have a what's their good property, that they are actually very fast temperature sensors, because their thermal time constant is very small. But they are highly nonlinear. They have very good sensitivity, but they are highly nonlinear. But you know that characteristic. So obviously you are not going to use that nonlinear measurement. So since you know the thermistor characteristic, pre-calibrated, manufacturer supplied data sheets, so in your computer you are going to linearize that data and then use it, right? So all these kind of processings, may be needed in a before you start doing anything with the algorithm.
So this is spike and outlier.
Well, they are the same. Roughly speaking, they are the same. Now we come to the data vector formation. That is, we want to now. So what I'm trying to stress at this is something that you need to understand, because of the fact that all the time we were talking about models which are yk is equal to ayk minus 1 plus buk minus 1, that kind of models. Are they the only kind of models? It is even if you accept that you need to use sample data, because you are planning to do it in a computer, you are not building an analog circuit which is a least square estimator. So you are doing it in a computer, necessarily means that you have to use sample data. But because you have to use sample data, does it mean that you have to use a so-called difference equation model? Yk is equal to something into yk minus 1. Is that the only model? Not at all. Even with sample data, you could use so many different kinds of models for the same transfer function. So just to, in fact, and it turns out that if you use the difference equation models, you tend to have big problems sometimes. Difference equation models are not good. They are not good in some respect. They are very nice to look at. You know, directly you are taking samples. You don't have to do anything. Plug that into the data vector. Data vector computation is extremely simple, just values of signals. But there are serious problems with the Z transfer function models, especially when the sampling time is high. Right? What are the problems? So before we come to that, I would like to emphasize that the underlying system is generally almost always a continuous time system. All physical systems are continuous time. Right? If it's a furnace, if it's a distillation column, if it's an aircraft, if it's a circuit. Right? So the system is continuous time. Right? Now, so ideally speaking, they are described by continuous time differential equation models, S transfer functions, if they are linear. Now, how do we get our difference equation model? By a process called discretization. Right? And so what do? Basically, we approximate continuous operators. You know, there are various discretization methodologies. We think that the only methodology is the Z transform. In fact, the Z transform direct Z transform is not a good methodology. Why not? Because it does not match the continuous response anywhere, because it's what is known as an impulse invariant transform. You could have discretization using an impulse invariant transform or a step invariant transform or a ramp invariant transform, various kinds of things. So without going into that, I'd just like to say that what model you get depends on a process of discretization, some process, and there are many methods of doing that. So this is the model that we have seen so far in the course, always, you know, yk, ayk minus 1. Now there are big problems in this. What are the big problems? Firstly, you will find that the parameters, see, there are some continuous time parameters here. Suppose you have a system y dot plus ay is equal to bu. This is your continuous time difference equation. This is your continuous, these are your real parameters. But the moment you come to a difference equation model, the Z transfer function model AB parameters are not only made of these ABs, they are also made of the sampling time. They are functions of the sampling time, and that creates huge problems. Why? We'll see. So what I want to say is that it's not necessary that you have to necessarily go to a discrete difference equation model. You could have various other parameterizations. For example, without going into any kind of generalization, let's see this simple system. This is the real CT system. We want to approximate this using samples, right? Because we are working with a computer, we need to approximate this using samples. I cannot get y dot. Who will give me y dot? I'm only getting y's, and that too at distinct points of time. So what's the simplest strategy? Write y dot k is equal to yk minus 1 by t. That's the simplest approximation of a derivative. So if you do that, you get this model. Now look at these. These are your discrete time parameters which you want to identify. They are functions of t. What happens if you are doing fast sampling? They all go to 0. So actually what happens is that, do you remember that this is the S plane and this is the Z plane. So this is the left half S plane. Where does it get mapped to? It gets mapped to the inside of the unit circle, right? So you see this is a semi-infinite plane, large, such a big area that gets mapped to a small circle, which means that if you have a small error here, it could mean a huge error here, is it not? So by due to noise or something, if you're and you are your system poles and zeros in your discrete time model, you are going to identify here. So suppose the true pole was here, and due to noise you estimated the poles to be here in your discrete time estimation. The actual poles and zeros of the continuous time system could go haywire. You could get double the steady state gain and things like that. People have shown. So these, especially at fast sampling rates, these models are numerically extremely sensitive. Little error will give you, after all, it is the steady state gain which is the reality. Whether you have got this, how you have got this parameterization is your problem. If your model shows a different steady state gain, you had it. Total controls loop, everything will go haywire. Either your response will suffer or your stability margin will suffer. One of them will happen. So now what is the alternative? The alternative is simple. The alternative is, can you not write the same model also like this? Just integrate between 0 and t, this equation. What do you get? You get yk minus y0 if you integrate y dot. Here you get a integral of 0 to kt yt. Here you get b integral of 0 to kt ut. Now can you not have a data vector phi which will be minus integral 0 to kt yt dt. This is one element. The other element is integral 0 to kt ut dt, and the other element is 1. And then what parameters will you get? You will get a, you will get b, which are the same as your continuous parameters, which do not depend on t, do not suffer from that problem, and y0. So you will also estimate an initial condition. See this you can very well compute using sample data. What's the problem? No problem. If your sampling time is faster, this estimation will go better, because your signals will be more accurate. So all I am trying to say is that, just because this needs to be said, because all the time we have used this kind of a model, but you must remember that you don't need to do that all the time at all. You need to just write an equation phi transpose theta, which is possible in many ways. Okay. So you need to, while you are doing this data vector formation, you need to know the parameterization. In terms of what are you going to write it? Are you going to write it in terms of integrals? Problem with integrals is that if you have a slight bias here in y, that is going to blow up. So maybe you don't want to maybe you don't want to use integrals. Use any other filter. Use a filter which will not blow it up. An integral is a very, it's an unstable filter. It's a marginally stable filter. Another big advantage is that this will have very little noise, because it's an average. So any noise that you still have it in y and u are going to get averaged and will go away. Typically you get very high accuracy on this, much higher compared to your discrete time models. And discrete time models have been used for more of a traditional reason. So having said that, you still have to decide a lot of things, like whether you are using an ARX or an RMAX structure, whether you need to model unknown deterministic disturbance. Remember that we said that if you have a sensor bias, then you could also estimate that bias. So you could model the disturbance, deterministic. You could decide that what is the model order that you want to select. So reduce it as you want, and you need to know whether there is any significant time delay involved. You know, unknown time delay estimation is a tricky problem which we have not considered. It requires other kinds of approaches. So in general, time delays may be there, but you need to spend some effort in trying to know them, and then using in your parameters. Otherwise, time delays lead to very high order models, because e to the power minus st cannot be approximated as a finite order transfer function sufficiently accurately. So you probably need to take care of it using a priori knowledge. Coming to the recursive algorithm, you need to choose your algorithm. What sort of algorithm? Recursive least square. Sometimes you would use, there are several versions of it. Extended least square, instrumental variable. There are a host of algorithms. Sometimes you have, you know, special kind of algorithms which have very good properties. So you need to carefully choose your algorithm. Since we have not read all of them, we cannot discuss them too much. And then you need to also think of various kinds of, you know, patches, smart practical patches that you want to put in your estimator for it to work well. For example, exponential forgetting, selective data weighting. You don't want to update your model all the time. If you have too little prediction error, it's good. Don't update parameters. You might save time. Similarly, covariance modifications. Do you like that your covariance does not die? Normal recursive least square, the covariance almost dies. If you want, you can keep it alive just to keep the estimator gain high, or you could go for a square root update to ensure that it always remains positive definite. No numerical problem. You could use parameter projection based on, always stable models. So anytime you get an estimate, check stability. If unstable, find the nearest stable model. So such things are needed, and they will give, sometimes they can give, what they can give is significantly faster convergence. You know, you are preventing it to go astray. Normally an estimator, if it once goes astray, it takes some time for it to come back to the track. If you closely monitor it and prevent it from going astray, then you tend to have faster convergence. That's very important, especially when if you are trying to use it in online, or you trying to use it for fault detection, because that will directly cut down your fault detection time if it converges faster. So after doing this, we hope that you got your parameters. Something came out of the algorithm at every time step. Oh, by the way, incidentally, it's not again necessary that you need to run your, how often do you need to run your parameter estimator? It's not necessary that you need to run your parameter estimator every sampling time. It's not necessary. You might run it every 10 sampling times, so you might run it. After all, this k need not be exactly the sampling time k. You only need to set up that model. They can be 10-20 samples later. Why do you, normally you don't need to, control inputs need to be computed every sampling time. Parameter estimates need not be, because parameters are generally much slower varying quantities. Similarly, post-processing and model validation. This we have seen in some cases. For example, recently we used a neural network estimator, which is a nonlinear estimator. Would you believe it? For estimating, we have actually used it. For if a carbide tool is actually cutting metal, it's getting worn out. So its cutting edge dimension is changing. Change is of the order of microns, 50 micron, 100 micron, 200 micron. Just by sensing vibration, motor current, we have been able to set up an estimator which can estimate that wear of the tool within 20 microns without measuring it at all, real time. Now, in such cases you will find that filtering of the parameters can give you a lot of benefits. That because the parameter estimate is definitely going to be jittery because of noise. Whatever, if there is any amount of noise, then your estimates are always going to be like that. Now obviously the estimate is not this, obviously the estimate is much slower. So after you got the estimate, it makes lot of sense to actually low pass filter the estimate itself, right. So you write theta hat filtered k is equal to theta hat filtered k minus 1 into alpha plus theta hat k into 1 minus alpha, and then you choose alpha equal to 0.9 maybe. So you see, every time you are not changing it, every time you are adding little bit of the estimated parameter. So you are actually doing an averaging, correct. Then you need to check before you hand over the model. Now you are going to hand over the model to whoever is going to use it. So you need to see whether there are possible model reductions, whether you need to eliminate measurement dynamics from it if you know it. Generally measurement dynamics could be available very well from the manufacturer's data sheet because the sensors are well calibrated and tested by the manufacturers. You have to do inverse scaling. Remember that you actually used a parameter in terms of scaled data. So obviously the parameters also got scaled. So now you need to do inverse scaling to actually come back to the units in which it will be useful. And you need to validate whether your estimation process is going healthy. So you need to know whether your estimator gain is dying, whether your estimator gain is corrupted. You need to check the prediction error to see whether it's white, whether it's uncorrelated with U, whether you have extracted all juice out of the data. You need to see all that. And sometimes you also need to detect parameter changes, because actually what happens is that this is a contradiction. Parameters are generally likely to be slow varying. So if you keep your estimator gain high, then it will become sensitive to noise and it will start oscillating like this. So while it is steady, you need to reduce the estimator gain. But if you reduce the estimator gain, then when it will change, you will not be able to track it fast. You can't have both at the same time. So what you should do is that you should have a separate mechanism of checking whether the parameter has changed. If you find that it has changed, or it's very likely that it has changed, you boost the gain. Otherwise keep it low, so that you have the best of both worlds. So such things you might like to do. Finally, coming to experiment design. Now you see that you have to design the experiment. You have to say what input you have to give so that you get the best model which will really suit your purpose. Sometimes if you are doing offline identification, there is one time you want to identify the plant, you can design your experiments. If you are using it in an online application, you cannot choose your experiments, input is coming. Like in adaptive control. In adaptive control, anyway the control is coming. You cannot suddenly give a sinusoid just to identify the model. You have to do it based on existing data. But in some cases you might. So actually what you have to do is, you must remember that you have to do experimentation needs to be done at two stages. As I said, that you first, to be able to have a good estimator, you need some a priori knowledge about the system and its environment. So you must plan your initial experiments to determine certain things before you actually go for data collection. So you need to know whether your linearity, time invariance, whether these properties are valid on that system. So you need to check that. Then you need to know whether it's stable. What are the rough ideas about the dominant time constants and delays? I mean, as we have seen that without these, it will be very difficult to choose a pre-filter. So you can't even implement your algorithm before you have some idea of this. Totally black box approach never works in practice. Then measurement and actuation dynamics, experiment duration. How much data do you need? Remember that in an actual setup, collecting data, if you go to a factory and say, can I try to identify your rolling mill? People will give you dirty looks, because because if you are going to identify that model for that time, he can't produce, his manager will shout, and people won't like you if you say, I want to identify your plant. So you have to be quick. You have to collect just the amount of data as you need, but at the same time you have to make sure that your job is done, because if you come back 7 days later and said, oh, I need another 20 milliseconds of data, that will not be pleasant either. So I mean, you need to fix experiment duration. So these are very practically important things, right? Then nature of noise and disturbances which might come, these things are very important. And then after doing these, you will probably be able to design a kind of a final experiment which will let you actually build the model. For that you need to choose your inputs, and while you are choosing your inputs, you must decide on the amplitude and the spectrum. Why? You must make the amplitude high, because that will make your data resolution high. You have to excite the system properly. If you make it too high, you might excite non-linearities. So you can't make it too high. So no clear guideline again. So-called quote-unquote engineering judgment. How high you need to, what is going to be your amplitude, and what is going to be your spectrum. Spectrum should be such that if you want to know what is the gain margin of your process, then you don't give a DC, because your gain margin is, I mean, your gain crossover frequency or your phase crossover frequency might occur at 5 Hertz. If you are looking for determining the correct phase crossover frequency, then you must excite it around 3 to 7 Hertz. If you give it 0 to 2 Hertz, you are not going to get your gain crossover frequency or phase crossover frequency correctly. And of course sampling time. So that's all. Only one point before we end is that finally remember that is all theory. Finally remember that you are going to code it in the computer. So you are going to need some computing time. You are going to need some memory. Are these important? As long as you are using a PC, not important. But if you are using an embedded controller, they could be very important, because embedded controllers are small devices. It might have 16K of on-chip memory. If you have written a grand algorithm, it could mean that it will require a separate memory chip. On-chip memory does not do, which will mean cost escalation, which will mean complexity of hardware, which will mean so many things. If you are a product designer, then it could mean between the success and failure of your application. So it all depends. Everybody does not use a supercomputer to be able to identify a model. So these could be issues. Finite precision arithmetic. You have to, when you are coding your numbers, especially in rudimentary processors, using fixed point, not too high word length arithmetic, you need to be careful about the truncation errors. Things which go under what is called the numerical carpet. There could be a lot of dirt there and could affect your results. Remember that, especially if you are going to use your results online for control, it's critically important. If I saw due to somebody had my algorithm gave a divide by 0 mid-flight, is not pleasant at all. You have to decide on update rates. Why? Because don't think that you are going to have a full processor to you just for updating theta hat k. The same processor is probably going to update 3 other control loops. So it's not, if it's not necessary, you should not update at every sampling time. It all depends on how fast your processor is, how many tasks you are scheduling on it, what are their sampling update rates. So it's generally actually what is known as a multi-programming scenario in which you are going to implement this, if you know what is multi-programming. And finally, coding. So hopefully I have been able to the best of my knowledge, I tried to draw your attention to certain various factors which really need to be considered if you want to get a successful model. So that kind of closes our identification module. Some of the major things that I want you to remember is that you must remember that the system is generally much more complex than the model, and selection of a model, actually the true model is actually a figurative thing. There is no such thing as a true model, and it all depends on how good an approximation you can make using resources which you can afford, and for the purposes that you need. So it's actually an engineering decision. There is no right or wrong here. Just like in most actual engineering decisions, there are only good ones and bad ones. Thank you very much.